It's been 5 years since NASA's TESS mission launched, and the spacecraft recently completed its first mission, fully observing the sky twice and finding hundreds of confirmed exoplanets as well as many, many more candidate exoplanets. So what happens now? The spacecraft is doing fine. There are still many planets out there to discover. Are there some new ideas for how TESS could maybe change its operations to observe different parts of the sky and maybe fill the hole that Kepler left when it lost its reaction wheels and really was unable to perform its primary mission? So my guest today is Dr. Nicole Colon. She is with NASA Goddard, and we spend a really great conversation talking about what TESS has found so far, what kinds of discoveries can we expect in the future in the field of exoplanets, and what are some really interesting ideas on how TESS could be used to change the way it makes its observations, maybe to try and fill that gap in the science pipeline that Kepler left. So enjoy the conversation with Dr. Nicole Colon. How is TESS doing?
Oh, TESS is doing great. So to explain what TESS is a little bit, TESS is NASA's Transiting Exoplanet Survey satellite. And if you hadn't heard, it's actually been up in space for over 5 years now, which is
That's
super
crazy.
exciting. Yeah, time flies.
And that feels like it was just yesterday.
I know, time flies. It was April 2018, the launch. I actually was there, and it was amazing. So it's amazing to see how far TESS has come in 5 years, but yeah, it's going strong.
There's no issues. Like the health of the spacecraft across the board is fine.
Yeah, everything is going well. I mean, every spacecraft has little hiccups here and there, and TESS is no exception. But every time it recovers fully, and it's just going along, chasing the sky, basically, and taking images. Continuously.
So, I scheduled this interview because we've reached the end of TESS's primary mission. So what was the goal of the primary mission?
Yeah, the primary mission was really designed to find exoplanets. So planets outside of our solar system, still in our galaxy. So basically relatively nearby if you consider how big the universe is. But I was designed to find these exoplanets specifically around the closest stars to us. And it really wanted to focus on, or was designed to focus on, I should say, finding small planets around bright nearby stars, essentially. And so that was the goal, is really to do kind of like a survey of what we call the solar neighborhood, like our friends in the neighborhood near the sun, near our solar system. How many planets are there, and how many small planets can we find? Because to us, the small ones mean, things like the size of our own planet, if possible, right? Like, can we find any small planets like ours, essentially?
But from my understanding, the goal was like scan the northern hemisphere one chunk at a time, scan the southern hemisphere one chunk at a time, come back around, do it again. That's the mission. That was the primary mission, right?
Yeah, exactly. It was only 2 years long. That's right. Yeah. So it spent a year surveying half the sky, essentially, looking really, it looked at the whole sky, but its focus was on studying the nearby stars, especially to find planets. But yeah, it spent a year doing half the sky in the north and a year doing half the sky in the south. And that was the prime mission, to get just like an all sky survey over 2 years. But now it's effectively been repeating that survey, because we've learned that there's a lot to gain from basically an all sky survey, just continuously monitoring the night sky from space.
So I think about the dynamics of planetary motion, that the transit method that TESS is using really helps you pick up those hot Jupiters, the ones that are orbiting very quickly, that the chances are very high. As you move into this next round, is the goal now to try and find the stuff that will have longer orbits, less likely chance of seeing in one observing run?
Yeah, that's right. So the nominal observing strategy for TESS has it observe any given chunk of the sky for about 27 days or so. So you're right. It's basically biased. Like in that 27 days, it'll see dips from a planet around a star. And so that means that if we're looking for multiple dips, that the planet orbits in much less than 27 days, right? So it's really close to its star. But now with, actually, right, 5 years of data, we're able to start looking at regions of the sky where we've observed for more than 27 days and, start to stack the data, if you will, and like just stitch it all together and get those longer baselines to look for those longer orbits. Exactly.
So if you had like some planet that was, say, orbiting every 5 days, then that would be very obvious if you're staring for 27 days. But if you've got something that's, say, orbiting every 20 days, you're only going to see it once if you're lucky, twice if you're lucky in that 27-day period. But if you stack up the two together, now you've got 54 days.
Absolutely. Yeah.
You're going to get 3 if you're lucky.
Yeah. Yeah. So people have been looking, for some of these events where you might see only one transit in a given observation period, but then they predict when you might see another one, and then they, wait a year or two for more test data and they check, did it transit again? And they're finding in some cases, they are finding planets with, orbits of hundreds of days this way, which is really cool.
Oh, that's really interesting. So they see a transit in that first run, and they know that the way things are lining up, they're going to be able to come back around and should see the next transit for some subset of the stars that they're looking at. They make a prediction. I mean, that's like science at its best, right? You make a prediction, what you should see, and then you see it.
Exactly.
Yeah. So, I mean, do we have a sense now with the survey that's been done so far how numerous planets are in our solar neighborhood?
Yeah, there's a couple interesting points to make there. I mean, so I have to mention, TESS is amazing. But the Kepler mission started it all from space, like in terms of, finding transiting planets from space. And the Kepler mission is what really told us that, like, it looked at an extremely small part of the sky compared to TESS, and it found so many exoplanets there that we could basically say that on average, like any given star you look at will have one planet. That doesn't mean every star has a planet, because some stars have multiple, some stars have none, but on average, right? So that's great if every star on average has one planet, because that means TESS should be successful, right, in its search of all the nearest stars now. And so what we're finding with TESS is that we have, over 300 confirmed planets so far. And a lot of them are very nearby. And so we're finding that compared to, again, Kepler, if you will, TESS is finding like multiple times, like twice as many or even 3 times as many planets as Kepler did nearby, because, again, Kepler was focused on one like small patch of the sky, and then TESS is looking everywhere. And so now, TESS is basically opening a floodgate of like, we didn't realize that all these planets were there. Like, even though we predicted they would be, now we're able to really demonstrate that they are, And so, TESS is finding, I think, I don't want to say more than expected, because that's not true, but it almost feels like that. Like, because we're like, wait, how did nobody find this planet before?
Because it was relatively close. There's a very clear signal as it's passing in front of the star. It is kind of interesting, like the ability to do photometry, to do the transit method. I mean, there are backyard astronomers that are confirming with their backyard telescopes, they are confirming exoplanet discoveries using relatively inexpensive consumer equipment. It's kind of surprising that the first exoplanet took this long, 1995 to discover, and with the radial velocity method, you would think that the transit method would have turned up planets first, and we would have known about it for years earlier.
Yeah, I think that's right. I mean, I agree. I think the case is that even though these like Kepler now TESS have been incredibly successful, and then ground-based astronomers or citizen scientists, they are also equally successful now at doing this. It's just that the the probability of seeing a transit is actually quite low, which tells you something, because it has to be the right alignment, right, for you to see the transit from our point of view. But then if we're finding so many transiting planets, that tells you something again about how common planets are, that we're seeing that many so easily, right, that have the right alignment to see them pass in front of their star from our point of view. So it's like, literally, it's like the stars are aligning, to give us these opportunities to study these planets from ground and space. Yeah.
So we talked about Kepler, and the Kepler was this flagship mission.
Mm-hmm.
And as people are aware, it lost its reaction wheels sort of midway through the mission. And so it wasn't able to complete the primary mission in the way that it was expected to, but still found more planets than any other instrument has found to date.
Yeah.
Do you think that TESS will catch up over time with year after year after year? Because like part of the magic of TESS, in my opinion, is the orbit that was chosen, that is incredibly stable, requiring no energy input from the spacecraft itself. Like, do you think it will catch up to Kepler over time?
Yeah, that's an interesting question, because with Kepler, there are thousands of planets that have been confirmed from Kepler discoveries, and equally thousands of candidate planets that have not yet been confirmed, but have been identified as possible planets. And a lot of the confirmed planets with Kepler were actually what we call statistically validated. So normally when we confirm a planet from the transit method, we detect the signal around the star and we see a periodic dimming, right? But then we follow it up with all these different methods. And one of those methods includes getting a mass of the planet, because that's like the bona fide, yes, this is a planetary mass object. It's a planetary size object. This can be nothing else but a planet, because sometimes it could be another star orbiting a star. So that's the issue, right? But so with Kepler, so many of its stars were far away and faint that we can't feasibly get masses. So people use statistical techniques to basically demonstrate that there's no other feasible possibility for these planets to be anything but planets. And that's great, and that's fine. That's like a commonly accepted thing to do in our scientific community. But that's how one way in which Kepler has so many confirmed planets, because you could just do this mass like validation using statistics. With TESS, we're 5 years in. We, I would say only have 300 something confirmed planets instead of the thousands that Kepler has. But it's only 300 because pretty much all of those have masses now. That's the difference. So people are taking the time to measure masses and confirm the planets rather than doing like these statistical studies. Not
right.
saying
And to get mass, like you have to do the radial velocity technique
so
to double check it.
Mm-hmm. And you have to wait, sometimes for the orbit. Like you need to collect data across the whole orbit to get the mass and accurately enough to say it's a planet. And so people are taking the time to do that with TESS. And so it's like they're more carefully scrutinized, I guess, in a way. It's just more rigorous the way that TESS planets are being confirmed. And again, I'm not knocking Kepler at all. I worked on Kepler too, and it's amazing. So it's just a different way you have to deal with these planets, because, with TESS, we can actually follow them up and get masses. With Kepler, we couldn't. But that's not to say that with TESS, somebody might come along and do like a huge bulk statistical validation and say, okay, all these candidates, because there are over 4,000 candidates still that have not yet been confirmed from TESS. So it's up there with Kepler, like in terms of the signals identified, see? So TESS has identified all these signals, but it's just that nobody has yet done like the work to weed through those and do a bulk validation and say, okay, these are nothing but planets, right?
So are the planetary confirmation tools scaling up as quickly as the candidate discovery tools?
Well, with some of the follow-up capabilities, some of them are like where we get high spatial resolution imaging of the system to look at the star and say, is it a single star system or is it a double star system? Maybe it's triple star, because that affects our interpretation of the planet. So we actually have a pretty healthy crop of facilities that can do that work. So that doesn't seem to be a limiting factor in confirming planets from TESS. But yeah, the radial velocities to measure masses, there are only so many facilities that can do this. And the thing is, it's all these facilities are more than capable of measuring masses of like giant planets, right? Like Jupiter size, even Neptune size planets, like 4 times the size of Earth. But it's when you get to the smaller planets that it takes, more time, because you have to monitor the star for a while to get a precise mass of the planet. And for better or worse, too, TESS is finding a lot of small planets.
Right.
So
yeah.
Even though even though the stars are bright and we can get good radial velocity measurements, it's still hard to measure the mass of a small planet, no matter how you slice it. So,
But it is interesting to me, like, if you sort of envision this as an assembly line, and on the one side of the assembly line, you've got something like TESS that is finding these candidates and then throwing them into the database. And then each one of these candidates, someone has to watch that one star continuously to potentially find the next time it gets a transit. If it's not discovered within that first 27-day period, then you're going to have to watch that star on its own. And if it's found 20 stars, then you're going to need 20 different observatories watching this one star. And then you're also, if you do find another transit, you're then going to need to follow on with a radial velocity measurement. As you said, there's not a lot of those capable yet, although there's more coming online. And then you're going to want to check the atmosphere, and that's like James Webb is busy, and aerial telescope is coming online. So I wonder, do you think that this pipeline is that changing the way astronomers think about how do we digest these planetary discoveries?
I think it has, or it is starting to change, I would say. I don't know if it has quite yet, but it's definitely coming to light. You mentioned the Ariel mission, for example. That's a European mission that's supposed to study something like hundreds or thousands of planets to study their atmospheres. And, TESS targets are all going to be great for that. But, we're taking the time to measure masses, and then, so that we only have 300 and Ariel wants 1,000, let's say, so how do we, maybe speed up that part of the pipeline, or is there a bottleneck, and what does that mean? I think people are also thinking about this in terms of other missions, because after the James Webb Space Telescope that launched in, 2021, is NASA's launching the Roman Space Telescope. And that's also going to find actually a bunch of exoplanets.
Right. But that's going to be throwing more to the front of the hopper.
Exactly. So that's the problem.
Yeah.
is it's going to find a boatload more, but then what do we do? Right.
Yeah.
And so I think people are starting to look at, TESS's pipeline, if you will, to go from candidate planet to confirmed, and think about how that can be more generally applied to other missions. So I know people are starting to think about that, but I don't know if there's going to be actions just yet. But that's definitely a thought, because it's bigger than TESS, right? It's bigger than, because with Roman and Ariel needs, and the European Space Agency also has the Plato mission that's also going to be looking at transit. So there's all of these that's going to add fuel to
and the Gaia mission is about to throw its next data release, and that'll be all via the astrometry method. So again,
so it's like, can you take what seems to be working well for TESS? There is a giant collaboration that goes through every step from candidate to doing all the follow-up that you can think of to rule out, anything but a planet. Can that be scaled appropriately for different missions, or how does it need to be scaled, right, or adapted or whatnot? So that question's definitely come up very recently in conversations I've been in.
Yep. Yeah.
Yep.
Yeah. It's like, sure would be nice if we knew if any of those are planets.
Yeah.
Right.
Exactly.
Yeah. And
So
it's like you don't want to let the candidates get too far out ahead of you.
yeah.
So let's talk about some highlights. What are some planets that you thought were really cool in the TESS first operation?
Yeah. I mean, I will say, with 5 years of data, it's hard to remember what came from what year at this point.
Sure. Yeah.
But, yeah, I will start by saying, in terms of cool TESS discoveries, TESS was designed to find all these small planets, again, around bright nearby stars, and it's doing that, and that's great, and that's really cool. But I've been really intrigued by the stuff that is not those types of planets, because I'm actually surprised. TESS has been finding a lot of giant planets still, and that surprised me because we have had ground-based surveys who also were studying and doing transit searches for years. And TESS has intriguingly been finding this population of giant planets around small M-dwarf stars, which is really interesting because M-dwarf stars are much smaller than the sun in some cases. And so the way we, understand that stars form and planets form, they form from this disk of material. And so with M stars, they often were thought to have like smaller disks of material around them, and then they would form a bunch of small planets essentially. So when we find a giant planet around a small star, we're like, how did that happen?
Right.
Or are there no other planets in the system? Did the giant planet gobble up everything? And what does that mean? It's for the evolution of these systems in the long run.
So almost like the gravity is so close to the star itself that you just get one big planet as opposed to a very diverse set of planets across a larger solar system.
Yeah, exactly.
Huh.
So that is something that was not really thought to be common at all. And now TESS has been finding enough that they seem, to be more common than we thought. So there's, I don't know exact numbers offhand, but there's certainly over 10 at this point, which doesn't sound like a lot, but it's still more than we expected, just from kind of when you think about randomly looking at nearby stars, and then if you extrapolate to other stars, then it's the occurrence rates of these things are higher than we thought. So that, like, as a general population, is just super interesting. So there's a bunch of those have been found. But on that same front, TESS has also revealed a giant planet around a white dwarf star. So that's fascinating because this is a star that is basically at the end of stellar evolution life cycle. So it's like the sun will die one day effectively, right? And it'll shed all its outer layers, and at the end of this day, there'll be left this like really, really dense white dwarf star. And the thing is, though, when the sun sheds its outer layers, we think, well, a lot of planets nearby are going to be destroyed because the sun's going to grow bigger, and then it's still an energetic process, the shedding, if you will. So we say, what will survive such an event? Well, now we have direct evidence that something can survive an event like that because we found a planet around a white dwarf. And it seems intact. It's not like a disintegrating planet or like, a rubble pile or something.
And close-ish to the star.
Yeah.
Right.
That too. So how did it get there, right? Did it... it couldn't have formed there, like in the first place. So it must have kind of migrated inward from a more distant orbit at some point, whenever that star used to be like the sun, possibly, and then it evolved, and then there was still enough somehow a planet survived.
Right. So it would be like getting Jupiter close into the inner solar system after the sun dies.
Exactly.
Somehow.
Yeah.
Right.
Somehow.
Right.
TBD how, right?
Yeah.
But yeah. And so TESS has shown us that that is possible, which is, really cool. And again, just raises more questions, if you will.
Yeah.
That's a good thing. That's why we do science.
What about things that it hasn't found? Like things that you were expecting to see, but actually haven't turned up in large numbers? I'm thinking about things like, say, the Neptune desert.
Oh, yeah. So that's an interesting question, that specific case. Because this Neptune desert, that's kind of like this range where Kepler and some other ground-based surveys, showed us effectively that there's this region where small planets kind of close to the star just don't really exist, right? That's the implication of this desert. But small planets being like, around the size of Neptune. So you could have smaller planets. And so the idea was that these planets kind of in this medium size didn't survive that close to the star. Like they would get their outer layers of gas stripped, essentially, and their atmosphere stripped off. So then all that was left was like a smaller core. But then the more giant planets, right, could survive because they have more mass to hold on to their atmosphere. So then there was this like in-between limbo that couldn't survive. Well, long story short, TESS is actually finding more planets in the Neptune desert than I thought too. So is it really that rare after all? I don't know. Like that's an open question. Yeah. So TESS keeps finding planets in the desert, put it that way.
Right.
And we're like, okay, so it could be again that, Kepler had some biases because it again only looked at one part of the sky. And so, could it be that it depends on the type of star that these planets are around? I don't know if people have really looked into that yet. Like we might not have enough, numbers yet still for that. Like, is it dependent, on the type of star essentially, or some other feature? But yeah.
Do you feel like the field is starting to shift from here are cool planets? And I could see, you had a couple of classes of planets that you're interested in, but it's getting harder and harder to think of interesting planets individually, specifically because we're moving to a larger statistical collection of planets. So is that sort of starting to make it hard to think about your favorite planet and shifting into these 1,000?
Yeah, it's funny. That's a great question, and it's a funny thing to think about because I remember when I was in graduate school and I was writing like my first scientific paper, and in the introduction it said something like, we know of like 20 something transiting planets because this was before Kepler launched when I wrote my first paper. Yeah. and so back then, point being, I knew something about every single transiting planet, like all 20, whatever. Like I could name all their properties, their temperature, their size, their mass, right? Like they were more individualized. Exactly. And then Kepler launched and you're like, oh my gosh, we have these populations of planets, right? But there are still absolutely like individual ones that we all know and love and study, a lot. But I think with TESS, part of, it's continuing that story that Kepler started of with the populations, like you said, exactly. Like it is more of a bulk thing, like giants around small stars and, planets around white dwarfs and these hot Neptunes in the desert and all that. But yeah, part of it is there's so many planets now. I can think of some that are really interesting, but I forget their names.
Right.
Like because I'd have to look it up.
Yeah. No, for sure. There's this one that we just reported on that it's orbiting at like 90 degrees to its star, and that's weird. But I forget it's TOI something.
Yeah. And in fact, just the other week, there was an awesome TESS discovery put out of a planet that might be like Io and have, volcanic activity all over its surface. For the life of me, I can't think of the name of it.
Neither can I.
But it's an awesome discovery.
Yeah, sounds cool. Well, Star Wars, it's Mustafar. So
Yeah,
I think
exactly.
so we'll just call it,
So we just name them all like,
name them all Star Wars planets and call it a day. Yeah.
Tatooine and Hoth and all. Yeah.
Yeah.
but
Yeah.
yeah, and so like it is absolutely super interesting that all these discoveries. I mean, TESS has found, well, one of its first discoveries was really cool. I do remember it was around the star Pi Mensa, and is because it's a naked eye star, and so it was just really cool that TESS could again find a planet around a star that you could see with your naked eye, and that's because we don't really have many of those. I think we have two.
So you're saying, like, if I go outside and I watch that star very carefully with my eyes, I might notice it dim every now and then.
You probably need really, really good vision and be able to stare for hours. But yeah, without blinking.
Now, one of the things that was most exciting about Kepler was it was going to be the machine that would maybe find another Earth, an Earth-sized world orbiting around a sun-like star. It was staring at the spot in the sky. It was going to wait long enough, multiple years, build up that data, find that other Earth. And then, of course, it lost its reaction wheels. And so it had to shift focus to the M dwarfs, and it wasn't able to make that discovery. Does TESS have that capability? Like, assuming the spacecraft lasts forever, 20 years, it's going to keep going and going and going. Will it eventually build up enough data that it could find an Earth-sized world orbiting around a sun-like star? I mean, the key is that 365-day orbital period, right?
Right, exactly. Yeah, because, I mean, to answer half of that first, it is, TESS has already found a few Earth-sized planets, right? But they're not around sun-like stars. And they, are equally interesting, for different reasons. Like some of them do have the right temperature to put them, where they might have liquid water on their surface. But they might be around, a star that's much smaller than the sun. So TESS has been finding those already, which is great because that also, like, it really wasn't designed for that. It was designed to find small planets around small stars in general, but not necessarily like in the so-called habitable zone. And so, I think with enough data, we've already seen evidence of some systems that TESS has discovered. There's been transiting planets discovered. And then with like another few months of data on that star, the data was able to reveal additional planet. And so we've been able to find, and these are all small planets in this case. I know the name of this one. It was TOI 700 system. So that's a really interesting system. But it has multiple small planets. And more TESS data clearly revealed another planet. And it's that kind of thing where I feel like we might need to look at systems that we know, like stars that we know already have planets, and like start the search there rather than kind of like a blind search for an Earth around a sun-like star, just because it's really hard to look at, for these signals. They're just extremely tiny. And like you mentioned, 365 days means, even if, well, let's say TESS lasted for 20 years, you could have 20 years of data potentially. But, stars change, which affects the signal over time. They have spots that come and go. So that can affect how well we can detect planets. The spacecraft could keep working, but some of its properties might change enough to affect the data quality over time.
No, it's going to live forever. Don't worry about that.
Okay. Let's say it's perfectly
perfect, beautiful, stable orbit, solar panels. It's great. It's doing terrific. Reaction wheels will last forever.
Yeah. So I think it's a matter of, how carefully can you stack the data to see those signals. But that's why I think, yes, if you can at least look at systems where there's already planets there, then that increases your odds extremely higher, to find additional small planets that could be Earth-like in the habitable zone, around the sun-like star. So I think that would be maybe the easiest way to do it. Not saying you can't just do, a routine search of all sun-like stars, right? But it's still really hard, like with Kepler. Kepler could do it in 3-4 years. with its data quality. But even then, people have said if Kepler just had like one more year of data, that would have made a world of difference. Because with 3 transits, you're like, okay, maybe 2 are noise. I don't know, like the odds of them being just noise increases, or some other artifact in the instrument.
But it does feel like there's a gap in that capability right now. Like when you think about JWST, even the Hubble Space Telescope as follow-on instruments for doing very detailed studies on something that you've already discovered, we're seeing incredible, analysis of the atmospheres of planets around other stars. This is all terrific. And then you've got this next generation of the ground-based observatories coming online with the extremely large telescope and the Giant Magellan Telescope. And so they're going to be able to really well categorize planets. But I feel like we don't have the targets yet. And TESS is one of the only missions out there that is gathering potential targets and saying, look at this, try this, what about this? I mean, is there a gap now for, like, if we do want to find that Earth-sized world, and I know exoplanetary scientists love all the planets, but you would really like to find an Earth-sized world orbiting a sun-like star in the habitable zone. Do we need a new mission? Is there something that would be the gadget to find those candidates that we could do the following observations? I mean, it was Kepler, right? Kepler is this Earth-sized hole in the pipeline. Right.
Well, I will say, I'll take my previous answer and shorten it down in the sense of, with TESS may not have been designed to do this, but people will absolutely try to do it anyway.
Right.
As the bottom line.
That's what I wanted to hear. Yes.
They will absolutely try to, no matter what. It's really hard, but they will still be looking at all the years of data to, and all the sun-like stars to see what small Earth-sized planets they can find. Like, people will be doing this. And I think, you're right. It is an interesting, thing to think about. Like, okay, what if people do try this with TESS, but aren't able to, make confident, right, discoveries? Well, given the amount of time it takes to develop new missions and, all of that, it's hard to say that that there would be a new one approved. I mean, you never know, right? Or if it's justified enough, sure. I think even though I mentioned, the Nancy Grace Roman Space Telescope earlier, even though that's got a very different design, it's really designed to look towards the galactic center and, different part of the galaxy yet again compared to Kepler and TESS. It's still expected to find a bunch of Earth-sized planets between its various detection techniques, actually. So we are going to get interesting information from that.
But aren't they gravitational microlensing? Like, don't you just get one shot at the planet and then you don't get to easily make follow-on observations?
So that is the primary mission. They're running the primary surveys, absolutely. But by sheer design of doing brightness measurements to get microlensing, it's going to actually, people have predicted it's going to discover hundreds of thousands of transiting planets, right? More than Kepler, more than TESS. Somehow, like, it's hard to fathom
as a side effect.
As a side effect,
right?
Yeah,
right. As loose change in the couch.
The caveat
hundreds
there,
of thousands of planets. Yeah,
exactly. And then the caveat there being that they're all be like in towards the galactic center, which means that it's incredibly dense part of the sky. So how do we confirm those planets, right? Like, we're confident that we're going to find large numbers, but are we going to find statistics there? And even then, Roman is also not designed necessarily to find these. It depends how long Roman operates as well, right? Like, okay, if it's looking at some parts for a few years, can you stack a few of those to find long period transiting planets? Probably, but again, it's not designed for that. So,
And it's not going to be necessarily comprehensively scanning the same spots of the sky. Like, I'm sure that there are plans to do let's watch this part of the sky, and then 1 year later, let's come back and look at the same spot. And then 1 year after that, let's look at the same spot and hopefully we find something.
Yeah.
But it's different than Kepler, which is just staring continuously at the same region of the sky. I mean, I think maybe people don't appreciate how much of a shoestring budget TESS is compared to some of these other flagship missions. It is in the low hundreds of millions of dollars compared to the many billions of dollars.
Right.
Is there room for a super, like if you were to like make a super TESS, what would you do you think?
Like, what would I do differently, or
no, like,
yeah.
Like, you know, if you're sitting down and NASA says, okay, like give us a super TESS, but don't go crazy, right? Just something that fall like, because I see TESS as like a pathfinder, that the orbit is wonderful. The capabilities of the spacecraft are perfect for what it's trying to do. But as I said, there's this gap in the pipeline. What do you think a super TESS might look like?
Yeah, it's kind of hard because, I mean, I want it to immediately say, well, you need, bigger cameras, bigger mirror, TESS's camera, which is not, the same as like Kepler's mirror, and that's different. And so, but then you also need to have that large field of view, like if you want to be efficient about scanning the entire sky. So it's like you have to kind of trade off. Do you want a bigger mirror, a large field of view, but is it as large as the original TESS, the field of view at one time? Do you then therefore have to spend more time scanning different parts of the sky, or like there's all these trades immediately that come to mind, right?
I mean, I guess, is it,
how do you balance that? Yeah.
Like, would you prefer a longer, like TESS is like 16 cameras? I'm trying to remember the number, but it has like a whole bunch of really
it has four cameras, but yeah, each one has multiple.
Right.
Like,
yeah. And which is different than a big telescope lens. Like they're each individual camera. So I guess, you could see fainter transits, which would maybe let you see fainter objects passing in front of the stars, or you could do a longer exposure, which would let you see more transits in the same area. But that's more of a, how do we point our spacecraft as opposed, so maybe a wider field of view with less turning, more cameras. If it was a ball of cameras, is that?
Yeah. I mean, people have thought about that for ground-based telescopes. I know, like they have all these innovative, they I don't even know how to describe what they look like a spider, like with 8 eyes, or I don't know.
Yeah. Well, it's like the dragonfly. There's definitely some stuff here on Earth that are huge collections of relatively inexpensive cameras. There's like 64 Canon Mark IIs bolted together. Right.
But then you imagine doing all that and making them like space flight ready, like the cost just balloons. Right?
So, okay. So that it's a ball, like a buckyball of cameras, all watching every part of the sky simultaneously, nonstop. Is that it? I
mean, it's maybe. Well, it's funny because I was thinking too about, so we mentioned Plato earlier. It says space mission that's coming up, I think towards the end of the decade, early 2030s. And Plato does, to my understanding, have this association with looking also for Earth-sized planets around sun-like stars. I don't really know their survey strategy, like if because I think they're doing more areas of the sky than Kepler did, for example. But I don't know.
Yeah, I clearly need to interview someone from the Plato team.
Because it's super relevant, first of all. But there's this whole idea again of like following up the Kepler, right? But not following up Kepler discoveries, but adding to that, right? And saying, yeah, Kepler started that, so let's keep pushing. And so whatever the Plato team is doing, I think will be a huge step, hopefully, in that direction as well. With TESS, I can say, I know you want it to live forever. It might.
Mm-hmm. I guarantee it. I just promised you. So don't worry about it. Yeah.
But formally, we are currently have funded operations through late 2025. And so then every 3 years we have to reapply basically to keep the mission going. But we also have the opportunity to change TESS's current observing strategy. So right now we're just kind of still scanning, flipping back and forth between north and south. Every 30 days, like kind of stepping around the sky. So we could adapt or change our strategy potentially to start like staring at some parts longer, to continue like
okay. So you could do like a 3-year mini Kepler where you just stared at one spot in the sky.
Possibly. Yeah. It depends on a lot of things, but yeah.
Right. Yeah. Then you don't get a chance to look at everything else.
Well, of course. Yeah. And then, making sure with the, again, with the orbit, you got to stay away from the sun. Obviously, you don't want to point at the sun as you go along your orbit. So, yeah, because Kepler was also in a very different orbit than TESS. So that helped it, observe one part of the sky stably for however long it did.
Right.
And so with TESS, there are ideas floating around like that. We could.
That's really interesting.
Change things. We don't have to keep doing the same thing.
Are there other? So say there are ideas floating around. I mean, what are some other ideas on how you might change your observing strategy to do different kinds of science? I mean, I sort of like this idea of the folks with the extremely large telescope saying like, we got nothing to point this thing at. We're waiting.
Yeah.
Right. Got the most powerful telescope humanity's ever built, and there's no targets. Yeah. So hurry up, TESS. So what are some other ideas of how you could change TESS? Yeah.
I think one reasonable idea is, so right now with TESS, it each 30 days, right, it kind of covers the sector or swath of the sky that goes up to one of the ecliptic poles, and that leads to a continuous viewing zone. So as it steps every 30 days, that ecliptic pole area is pretty much continuously observed already. So there is a part of the sky that we do get long time baseline.
Right.
And so an idea has been, we could shift further away from the ecliptic plane and have more kind of focus around the continuous viewing zone, like just kind of shift the entire field of view north or, south, I guess, depending which hemisphere you're in. And so just kind of shifting the part of the sky that you're in, but to get more coverage near those continuous areas that we could stare at effectively longer.
So you'd lose a little bit of your equatorial region, but now you would have this larger overlapping poles that is being observed for an entire 6 months.
Yeah, or it depends, how long, but it could be, even, a year that we're getting a good chunk around the pole, compared to right now we'll get like one camera on the pole. We could get like 2 cameras around the pole or something worth of data.
That's really interesting. I like that idea a lot.
That idea's floated around, yeah. And so it's stuff like that you could do to adapt TESS as is, like without launching a super TESS. Or,
so you're declining my offer of the super TESS then?
Well, I'm not declining.
Okay. All right. So
there's always creative ways.
Well, just put my checkbook away then. And so I guess what is next? I mean, are there some interesting announcements, any interesting things that people should be watching out for in the coming weeks and months with TESS?
With, I mentioned, we just missed it. There was that really cool volcanic planet result that just came out. But I think a couple interesting things coming up include actually TESS. So this goes back to the prime mission days, actually, but TESS and the K2 mission, Kepler's follow-up, they overlapped in observation time for a very brief time period. And so we have data actually from both observatories, and that has helped us, not me, but some scientists find some of Kepler's final planets, if you will, and TESS was able to contribute to that. So that's kind of cool, like a nice passing the baton.
Yeah,
again.
but also provide some calibration.
Exactly.
Yeah.
So that's fun to think about. But one thing I'm personally excited about with TESS moving forward is, so as TESS moves on its observations, this coming fall, it will be observing actually towards the ecliptic plane again, which it really hasn't done much of. We normally avoid a lot of that just because there's a lot of like scattered light or stray light from the sun that, just affects the cameras and the data quality. But we're able to observe the ecliptic this fall, and we'll actually be observing the star TRAPPIST-1 for the first time ever with TESS. And TRAPPIST-1 is infamous for having 7 rocky planets. And so I'm really excited to see what TESS shows us for TRAPPIST-1. We're only observing it for one 27-day chunk, but I'm hoping we'll see multiple transits of the planets and be able to contribute to that story, because TRAPPIST-1 is also a heavy JWST target. So I'm excited to see what comes out of that.
Yeah, we've gotten one observation announced from JWST so far. Like, clearly they're going to turn this into 7 sequels that we're going to have to wait.
Oh yeah.
One planet at a time.
There's more coming. And yeah, I'm involved in some of that too.
Oh, okay. Did they?
Yeah.
I guess you gotta wait until the embargo lifts. But
yeah, well, some of the data hasn't even been taken yet. So the one program I'm involved in for TRAPPIST-1, the data is starting to come in actually in June. So we haven't even gotten our data yet.
Yeah.
So we're excited. But so that's why I'm excited, because TESS ties into that story now. One of the most famous planetary systems, and TESS will be able to contribute. So that's really cool. And then that's when TESS is starting. Actually, it'll be starting its 6th year of science at that point, which is crazy to think about. And so I am excited to see what else we get out of these ecliptic observations, because they're covering now fields of the sky where the K2 mission observed again. And we haven't been able to revisit those areas of the sky before, for 5+ years now. So K2 found a lot of interesting targets and planets, especially around young stars and in star clusters where stars have just formed. So that's another population of planets that TESS has been contributing to, that I think is going to be really fascinating to see all the young planets that TESS can find moving forward. And some of them might be, ones K2 already saw, but I think the few that K2 found tells us that there's many more waiting to be found again. Mm-hmm. So hopefully TESS will be able to support that. So I think a lot of that's going to come out, in the coming years, because of this looking towards the ecliptic, which is, the opposite of the pole that we were talking about. Like if you stared at the pole, but it's see, that's why you have to balance. Yeah.
Well, hopefully we'll come back in 20 years and you'll let me know how TESS is doing still, and we can celebrate the launch of Super TESS. Nicole, thank you so much for taking the time to chat with me today, and congratulations on success of the first observing run, and here's to many, many more with TESS.
Thank you. Thank you so much.
All right, take care. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Shipolin, Jay Dennis, David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.